Welcome back to our data structures class at Riga Business School, part of Riga Technical University, and today we will look at AVL trees in our data structures class. It's a type of self-balancing tree, and so we have looked already at red-black trees, and we have already looked at the regular binary search trees. So what's the problem we are trying to solve? Again, let's recap. Again, let's do a visualization. Again, perhaps I will do already have a visualization here. So over here you can go University of San Francisco, I believe it is. We have visualizations. So let's look at our binary search tree visualization. Let's see, I insert some numbers as a basic binary search tree, right? And they're ordered, right? So remember what the problem is. We are inserting numbers in order. We have a binary search tree. Let me increase the speed a little bit, right? And well, what do we get? Unfortunately, we get something which is the extreme, the worst case scenario. We get a linked list essentially, right? So none of the cool efficient operations we can do on a binary search tree, they won't, it will degrade the performance to just regular linear search, which is not what we want. Right, so we need the way of balancing. Again, let me delete everything, let me restart, and let me do something also. Maybe I want to go down. Let's see, 20, 18, 16. Again, same problem, just different direction, right? Same direction. Again, so these are quite common scenarios. You have a ascending or descending order of elements, and you're inserting, and well, you get this bad performance. Of course, one solution would be to have a random insertion order, right? But again, if you're doing it live and not in it's online mode, meaning you have incoming data, well, you don't have this luxury of doing random insertions, right? So again, maybe slightly less common case is when you insert things increasing and decreasing. Let's do 20, right? And let's also insert 2, right? So far so good. I'll insert 18, right? See? And insert 4. Again, this might not be as common, but still leads to the same problem, right? Because I'll go down. So I'm going down from both sides, and I still have the same problem. Why? Because, again, I still have a linked list, right? You can see if you stretch this out, it's still a linked list, and I can keep going, of course, right? And again, so it's not random, but it's not also ascending. It's actually, we have a specific way of doing it, but again, we are degrading our performance, and it'll be just same as ascending or descending order. Again, this is just binary search tree, right? So it meets all the properties. Left side is always less than the right side, right? So for each subnode as well, right? So this property holds, but again, in order to reach this property, our tree performance degraded, right? So we need again, usually we will want a self-balancing search tree. Idea being we do some balancing on occasion. Maybe, to prevent this type of degradation of this inefficiency, we want to open some conditions, we want to rebalance. So there are many different self-balancing trees, different strategies, but AVL, the one we're going to look today, is actually the first published paper in early 1960s, I believe 1962 actually. It is invented by two Soviet mathematicians or inventors, or you call them, not probably data. Computer science was a really new field there, right? And it's named actually AVL for their names. I think it's Adolf Sonvelsky and Yevgeny Landis, right? So two inventors, AVL, right? So, and it is not as common maybe as our red-black trees, because red-black trees are slightly easier to implement, right? But we'll see it's not that bad, but it's actually for many operations, AVL tree will actually give you slightly better performance. If you look at our big O cheat sheet, right, you see our binary search tree, of course, has a problem at this worst case excess, right? However, AVL trees and red-black trees, the in big O notation, right, average is theta log n, for all operations, and worst case is O log n, so upper bound, right? So not bad. Of course, like I said, AVL will generally have better constant for access. Actually, right? If you worried about access, the AVL will slightly have better access. Why? Because red-black trees don't have such a good balance as AVL. So the rule for AVL basically is to keep track of the balance factor for all nodes. Well, let's take a look. Let me do something. Let's do 10, right? I'll do 12, right? Okay. Now I'll insert 14. So if we had a regular binary search tree, if I insert 14, it would stay here, right? It will go here. However, what do you think will happen with an AVL tree? There will be a rebalancing. The rule is actually quite simple. No node can have left or right side height differ by more than 2, right? So let's take a look. So more by 1 basically, right? So we have a one child, right? Here, let's insert 14, right? And we are gonna rotate. Notice, look at this. It rebalanced. Kind of cool, isn't it? Right? So, of course, the difficult part is to learn all these rules for rebalancing. But okay, let's do again. So I'll do 16. How are we doing? Okay, nothing changed. So now the depth, the height difference between children, right, is here, well, you can say 1 and 2, basically, right? Depends how you calculate the height here, but basically the difference should be no more than, you can have no children, right? Or at least no more than 1, basically, right? The height wise. All right, let's do one more. Let's do one more, 18. So what will happen when we do 18? All right, look at this cool stuff, right? So there's some cool rotations going on, and hopefully in today's lecture we'll learn how they are accomplished. Again, implementing this in a program is relatively, well, again, as long as you know what to do, not too hard, but it's easy to make a mistake, of course, with these rotations. Using pointers, of course, could be quite difficult. Okay, so let's do, so we see that everything's fine. If we insert something here, let's insert again. So will it require rebalancing? Well, we'll see. I'll do slowly. Insert 20, right? So we find, of course, now the first step is easy, right? Just like in a regular binary search tree, we find the right place. But then we need to check recursively, go up and see if there's any rebalance needed. Well, here we see no problem, difference 1, nothing, no problem, nothing to do here, right? So, right, doing height, unwinding, 3, and now there's a problem, right? This has a bigger difference height, and this has smaller, right? So we need to rebalance, right? Right, so we need to rebalance. Wow, look at this. So this is one of the rules, how we can adjust. So the key part is we rotate while keeping the binary search property. Again, notice these both are valid binary search trees, right? You see the difference. Every node less is under the left side, right? Every node to the larger is to the right side, and this rule holds for all sub trees, right? So no matter which tree you take, the rule holds, and this still holds here, right? Anything to the left is under here. 14 is less than 16, right? The grandchild is less than 16, so it's a very important rule, right? So that's why, so it's a little bit tricky how to implement this. So there are about 6 rules roughly used for rotation. We will learn them all, at least we'll go over them. So hopefully you get the big idea. So we have some rules to adjust balance if the balance is broken by too much, basically, right? So the balance is basically quite close, right? So again, our weight is balanced, basically, right? So you need to have at least the height difference basically cannot be more than, you cannot have a height 2 somewhere here and a height 0 in the other side, right? This is fine, right? There's not much difference here, right? So, for example, this one here has nothing, right? That's fine, of course, right? You can have left side. So you can have a left side heavy, or right side heavy, of course, right? It's completely normal, right? Okay, there's only thing that might be confusing, the way this is done here. Literature usually use different naming, right? Here you can see the height, but it's not really height, it's height plus 1 actually, right? Because height is 2. Height is 2, height is 2, right? Again. Alright, let's look at slides. We're going to be using slides from our colleagues at the University of Washington, David Kaplan from AVL trees, and let's take a look. So, balance, right? So, it's actually can be proven the balance maximum height will be 1.4 log n, right? So, if you have, so balance means what? Height of left subtree, height of the right subtree, right? If you have 0 everywhere, it's perfect balance. If it's small everywhere, which is what we are going to do here in these AVL trees, then that's, balanced well enough. Again, it can be proven if you use this rule of AVL, where -1 and 1, basically the differences between the heights, right, is either 0, -1, or 1. You cannot have more. In our example, right, you can check, right, there's no difference, 0. Here you have +1. Do we have any -1? No, we don't have any -1. Let's insert, let's do -8. Let's insert 8. Right, no rotations, let's insert 8. Will we have a problem? Let's check. Well, I don't think we'll have a problem. Let's take a look. Right, we find the right place. Okay. We do have a problem, I think, right? No, we don't have a problem. No, we are fine. So we are fine. Okay, so why are we fine? Because no matter which node, which subtree we take, right, there's no balance, the difference is no more than 1, right? So here you have a strong left balance here, right? You could say -1 if you want to say, okay, this is 1, there's nothing here, right? Here you have right side imbalance, but this only applies to this particular root. No, if you consider this a root subtree, right? Here you have no problem whatsoever. Well, this has 0, 0. This one also is slightly imbalanced because, of course, this has 2, height is 2, this height 1, right? Again, here, same thing goes for here. The height is, well, 3 and 2. Again, difference is 1, left side heavy. However, this one is right side heavy, 1. But again, the rule is not broken, right? So again, you need to check recursively whether the rule is broken anywhere, right? So that's how AVL3 ensures that the height balance stays, relatively, the tree stays relatively balanced. Okay, so that's a big idea. Now, let's see. Right, so like I said, the balance property has to be -1, at least 0 or 1 basically, and depth is basically log n again. So you need to keep 3. So binary tree property, of course, binary tree, well, that's easy to keep because 2 nodes, 2 children, or 0, 1 or 2 children, that's allowed, right? No more or no less. Well, you can have negative children, hopefully, right? And search tree, binary search tree property, of course, that again, notice in this case, is it true here? Is this a binary search tree? Well, 8, 5, 6, 7, it looks like, okay, 2, 4, 4 is less than 5, that's correct as well. Again, sometimes it's tricky if you forget, about this binary search property, right? If this was, let's say, if you go down here, could this be, let's say 7? Well, no, because 8, right, anything to the right side has to be more than 8, right? So 7 cannot go here. If you need to put 7, it has to be here, right? So because it has to go on the left side somehow, right? So yeah, that's a little bit tricky again. So same thing here. You cannot put like you cannot put can you put 8 here? Well, because 8 is less than 11, you cannot, or even 9 or 10, right? Because it's less than 11, it has to go on the left side. So same rule again. It's recursive rule. It applies to every node. All right. So let's continue. Right. So we keep the height. Well, again, so this height property, right? So data, of course, is just any data. It could be a pointer to an object with data, some structure. Really, it doesn't, for our purpose, doesn't. Well, it matters because we're using the sort, right? If we're using integer to sort, of course, right? Some sort of one of the properties for sorting, right? You will need some way of sorting. But yeah, so not only sorting, but I mean comparison, right? So left side, right side. This is binary search tree property, right? Again, so notice difference between this and this way, right? Here's use for. I don't like this way of writing because this is not really a height. Height is technically 1, 2, 3, right? It should be 3. It should be one. It should be one less actually, right? Everything should be one less. This visualization is the best one I've seen, but unfortunately the height, they use slightly different height, so they count how many, right? Here the classical way of classical doing is the actual height, right, as in original paper. So again, why is height 3? Because 1, 2, 3 here, right? So how here, right? You have 1 and 2, right? Maximum height, right? So because one, both, so 0 and 0, right? So we check the difference, 1 and 2, no problem, right? It's +1, right? Here same thing, +1, right? This has children, this has no children, so again +1. So that's how the imbalance is achieved, right? Again, at no point in this binary search tree do we have a imbalance greater than 2, right? So we are fine, and this is a legal AVL tree. All right, so these are two examples of which are not AVL trees. Again, let me check time, how we're doing on time. We're doing good, so I think we'll be able to finish this. And so again, you see here at this level, the problem is here. Up to here is fine, right? The problem is this imbalance at this point. Well, you can say first level. This is the root level. This is the first level, right? The left side has no children whatsoever, so no height, 0 height. Right side has, well, 2, so imbalance is okay. If you subtract 0 minus 2, obviously it's minus 2, right? How about this side here? Here, right? Again, the problem is here, the 2, right? Minus 1, right? There's nothing here, right? Basically, right? There's no children whatsoever, right? So imbalance is again minus 2 again, right? You can say, of course, height is 2 because there's height as well. Is there? You can minus 1. There's no height whatsoever, right? So minus 1 here, right? So empty 3. So note height empty 3 is minus 1, right? If you have nothing here, right, which we don't have anything, right? So we will have a imbalance again. But I think also intuitively you can see, of course, this has 2, height is 2 to the left and nothing to the right. Okay. Hopefully this makes sense, right? So now we can slowly get to the way of goods. Okay, so the best case scenario is if we insert something and the balance is preserved, right? So small, middle, and tall, SMT, basically smallest, smallest, middle, and tall, right? So balance preserved, right? That's what we're hoping for, right? So again, let's look at our example. So where would the balance be preserved? Any place. Here I can insert 11, right? This will not break anything, right? I'll insert 11. Right, we just find the right place, left, less, more, and we're fine. Again, now we go recursively back, unwinding the recursion, checking the heights, and there's no problem. Okay, so that's the right side. Same goes for left side here. We can do it here, right? Completely fine, right? What can we insert here? 15, no? 17, not 15 would go here. We can do that, of course, as well. So question is now, would 15 break anything? I don't think it would, because why? Well, yes, actually it will break. No, let's think. No, it won't break. Let's think. Let's do 15. Okay, so nothing broke. Again, this is not complete, right? Of course, but the balance, no matter which child level you look, at which subtree level you look, the balance is preserved. Again, 2, 2, 1, 1. Okay, so there's not something missing, that's fine, right? Of course, if I deleted this 20, we would need some rotations, for example. Okay, let's insert 17. Again, so this is the best case scenario. You just use this regular binary search tree, you do nothing, right? So it will go here. And we are fine, right? Again, so we can keep doing. So we can, of course, could we have anything we can insert here? Well, you could try insert 16. What happens if we insert 16? Sometimes some rules are defined if you have doubles, right? Can we do it? To the right side. So it will go here, right? Technically, if it's equal, go to the right side. Again, usually so equality, right, is preserved. You know, if it's equal, you go to the, consider this larger, so go to the right side. Of course, it depends. You can do, of course, do it left side as well. The tie breaks are always interesting. So yeah. So how about 17? Probably 17 will go here as well, right? Yeah. And still, we are fine still, right? Of course, we're doing great. Okay. We can, of course, insert some more. I'll insert like 30. Again, these are all best case scenarios, right? We have to do nothing because the balance is preserved. All right, now we get to the bad cases, right? And these are the tricky ones. This is why AVL, well, I would say it gets a bad reputation because they are hard to handle, right? So, but they're not too horrible. So bad insert case. So if you have a left or right side imbalance, of course, these are mirror images of bad imbalance. So right, so left child, right, so, you know, left or right imbalance. So this is right imbalance, right? So because you have to height 2, but there's nothing here, so of course this is a problem, right? So what's the solution, right? Remember, if this is larger than S, so obviously this could be a child here. So that's the solution. You can move the parent, right? Move this up, and this becomes a child of this middle, right? And it preserves everything. The invariant of the binary search tree, you have an invariant property of having a binary search property, right? Is preserved, right? So let's try to look at it. Yeah. So like I said, a single rotation. So this is a basic operation, right? So a right child, right? This is the right child, can have it's legal to become parent. The right child becomes a parent to the previous parent, right? Maybe not, hopefully not in the real world, but well, maybe in some legal sense you can be a guardian to your parents, maybe. But yeah, so this is what's happening in the AVL world of binary search trees. Again, so let's see, where could we get this imbalance? Well, I'll insert 40. So how much rotation do we need to do? Well, only here, right? So what will happen? What do you think will happen? Let's think about this a little moment. Take a moment to think. So we'll have a height imbalance. This is 2 and there's nothing. So 0 over 2. We'll need to. This will become a child of 30. Parent becomes child. Right side child becomes parent, left, so parent is left, so it goes here, right? And of course 30 will be still greater than 18, it will move up. So that's exactly what's going to happen. I'm pretty sure. This is very good. Adjusting height after recursive call. Look at this here. Like I told you, right? See how nice, right? Again, so our tree becomes more balanced, and we are good. We are good again. Pretty good, right? Not so scary at all. Let's do left side. Why not? Let's do left side. We have some numbers left. Let's do 6. So will we have any problems here? First of all, 6 does not present any problems. It's a good case. This is still a good case, right? We don't have any balance problems. Let's do 4. So, again, same idea, except to the left side. So 6 will move up, 8 will become a right child of 6. Right? You can move it up, and 6, of course, has to take over duties of being a parent and it will be the child of 10. And as you can see, let's wait for the magic, and let's rotate. There you go. You see? And again, the invariant property of binary search tree is preserved. Alright, how about that? Alright, so that's a single good rotation. Will we have any more bad rotations? Right, so general bad case. Right, so this is generalization, right? Left-left being balanced, right? Again, this may be not as clear. I think that these are more clear, right? And you basically adjust it, basically, right? You move it. Yeah, so you rotate, basically, right? So height of left subtree will be same, right? Height of all ancestors, and we can stop, basically. We can stop here, right? And our imbalance is solved, right? So B becomes unchanged, or B becomes a new parent. Okay. The question is now, if you rotate this, right? What happens? Sometimes, you know, you can have a what do you do with this? If this B has to rotate up, right? What do you do with this child? It has to move here, right? So that might be something that's tricky. Let's see if we can get this tricky case. Let's see. Let's see. Well, with zigzag, I can try and see some bad case, maybe. Well, we don't really have it here, actually. So yeah, we'll get the deletion afterwards, maybe. All right. So now we get a zigzag. So the zigzag case, you know, something like this. So how do you fix this type of case, right? Left-right or right-left imbalance. This type of imbalance. How do you fix that? We can get it here. Let's do it here. So we will fix it here. Let's do, well, what can we do? 14? Or maybe we'll add it here. I'll do it here. I'll do like 50. Let's insert 50. No problem, of course, with 50. That's a good case. Okay. So now we'll insert 45, right? And it will still be, then it will create this imbalance. All right. Let's go down. So 40, but 50 is so right side, and we have to go left. Okay. So this is not all, again the same problem. 4 to the number 40, right side height is 2, left side is 0, so we need to rebalance. So how can we rebalance? It looks like we can do 40. It will be the grandchild will become a parent, and the previous parent, the grandma, will become a child now, right? So 45 will move up and 40 will go to the left. Indeed, again, as you can see how it goes. So the grandchild became a parent. Pretty cool, right? And again, recursively, we don't have to do anything else. All right, so that's the case. So left-right or right-left imbalance, we fix it with a single rotation. Right. Well, they call it double rotation. I call it single. Well, it's not a. Well, we accomplish this in one rotation, but as you can see what happened. So the grandparent, right, moved up to the middle, right? You can see here. Here I call it double rotation in this literature, right? Yeah, you can think of these two rotations. You know, going up twice, right? So middle, yeah, you can do it 2, and then you yeah, by reducing to the previous, so by rotating to the middle, right? And then you rotate up as previously, right? That's also, if you want to think of it like this, that's fine. I think it's also easy enough to see it here. Well, right? Well, as you can see, it's 2 rotations technically, right? But maybe not that much different. All right. So we're almost finished with the easy, good and bad cases. I mean, with the easy bad cases, right? We will need to look at some deeper cases in a moment. Let's take a look now. Yeah, so these will be, again, to this generalization, left-right, generalization, how to achieve this, right, and fixes the imbalance, right, zigzag, right, zigzag rotation, right. So find insertion algorithm is find spot for value, hang a new node, search back for looking for imbalance. If there is imbalance, either perform single rotation or double rotation, and the good part is there can only be one imbalance, right? So this is pretty nice. So insertion, we have made an insertion algorithm for AVL3, right? So again, this is an abstract data structure. So we have typically one insertion, right? Again, search, of course, search is covered by binary search property. The only what we'll need is, of course, we'll need deletion, right? That's maybe slightly trickier, right? We'll look at that after the break. So easy insert, of course, right? So easy insert, of course, right? So hard insert, you can look at some examples, what we just did, right? So insert 33, right? And we will need to rotate up, right? So 33, right? So we rotate the imbalance, so only one, right? So let's look at this example here. So if we insert 33 here, right? We have 33. The question is, where is the imbalance? It's not here, right? It's actually upper here, because you have a height 1, 2, 3, you have 1, so you have to rotate this number here. So 15, right? So rotation happens here, not here. That might be slightly harder. Let's take a look. Can we get it here somewhere? We are fine here. Okay, yeah, here. This will create this imbalance. So let me insert 60. See, the problem is not here, right? Not here, obviously, right? You know, but moving up, right? 2, 3, 1, right? And here the problem, right? 1 and 3, again, that's a cult, right? So this is, so what will rotate? Now let's think about this, right? So we need to fix it. So 45, well, will move up, right? Right? Then 30 moves down and attaches the 40. So what happens to this 40? If you're moving up, right? It will become the right child of 30. Let's take a look. So this rotation is these three. These three. Check this out. Wow. Right? So again, we preserve the invariant property of being a binary search tree, but it's the same zigzag operation, only it doesn't happen at this level, it happens like a couple levels higher. So again, like I said, 30. And again, so 40, right? It was attached to 45, it's now attached to 30, right? It's the same rotation, right? So why can you do this? Again, because binary search property guarantees everything to the right is larger than this, right? Including the subchildren. So we can safely attach 40 to the 30 here, right? And again, this preserves the binary search tree property. Again, so again, this insertion, again, the good news is this insertion only happens at one place, right? So that's good news for you. All right, single rotation. Bad case 2. Let's see, can we get in bad case 2, insert 18. So here, right, again, let me see if I can do this. Where can we get the imbalance? Let's try it here. Let's try 7. If I insert 7, it will be very similar actually. No, if I insert 7, it will be also a bad case, but it won't be. Okay. So no problem here, just difference 1. That's allowed. Here also no difference. Problem will be here 1, 2, 3, and 1. Right? That's will be a problem. So what will happen? We're going to do a rotation. Right? Yeah, that's right. 4. Right? 3, 1. So 6 moves up here, and we have a problem with 10, right? 10 moves down. Let's take a look. Wow. Right, so 8 moves up. 8 moves up, right? 7 attaches, so these 3, right? So 7 sticks with this one, right? So again, so quite again it gets complex, but of course, again, remember this only we moving on 3 elements attaching. So again, rest of the tree is not unaffected. So while it's complex, right, to follow this through, but otherwise the rest of the tree is not affected by this rotation. Again, it's a single, well, you can call it double rotation, but it only involves 3 elements, right? So 7 is attached to 6. Well, you can say, okay, 7 is also attached to 6. No, this also is the pointers involved are actually for 4 elements, right? How about 11? Well, 11 doesn't care, because 10 still is the friend of is a parent. It's still 11 is still a right child of 10. All right. So 8 moves up. So this is the second hard case. All right, and again this preserves the property. All right. In the second lesson we will look at deletions and some more hard cases in AVL trees. Thank you, everyone.